almost lunchtime, so let's go very quickly into the seminar. The title is Multitemporal SAR Concept and Application. This is our agenda for today. Yes, we start from the visualization of data. We will explore both bitemporal visualization and multitemporal visualization, and this will be the sort of the tool that we use to explore this sort of time machine that will bring us from the 80s, in which the data were elaborated using, let's say, traditional image processing, up to modern AI. This is the global scenario. We have two kind of products that we can use. We have SLC products, so they are coherent, in which the phase information is available, and then we have incoherent products, so they are higher level products that are already pre-processing, in which the phase information is lost, and we have just the amplitude. We can use this kind of images in basically two applicative scenarios that are the bitemporal change detection that deals with abrupt changes or emergencies in most of the cases. And then we can explore the full time series to make analysis like AGB, deforestation, or land tracking. And as I said before, we can use basically three methodologies to process this data. So we have the traditional image processing, then the machine learning, and the AI. I want to highlight that it is not that the newer the better. We will see that in most of the cases we can obtain outstanding results using very simple technique belonging to the category of traditional image processing. Basically, it depends on the application, and we will give an example of when this technique can be used to tackle different applications. So let's continue with the global scenario. This is the whole workflow of data analysis. We have our satellite that acquires the raw signal. Here we have a ground station that receives the signal from space. It is processed up to this kind of signal are usually called of level 0, so they are unfocused. They are usually focused at the ground station, then they are delivered to the places in which we download data, and this is typically our entering point. So we are working with the level 1 products that can be both coherent, so both SLC and GRT. Then we want to extract information from this product. So we have this big jump from the level 1 to the level 2 that can be a product of different nature. I put here some examples, but there are many other. The question is that when we work with SLC data, so with level 1 data, we have this kind of representation that can be quite confusing. I'm not able to mine too many information from this kind of images because they are basically black and white. We are not used to deal with black and white images. There is speckle, so there are a lot of problems that prevent us from mining the information from data. So the question is, can we use time series data to make to build more comfortable visual representation of data, and maybe something that can be useful for processing? So let's see how we can explore time series for building this kind of representation. We will start from pure change detection, so from the visualization of the bitemporal data, and we consider a very favorable condition, that is the one of semi-arid environments. That is, in this case, we are in Western Africa. So we are in Burkina Faso, in which there is a very good separation between seasons. So we have a dry season that lasts almost all the year, and we can see here that precipitation, so rainfalls, are concentrated in a few months. So we have a very long time period in which the environment is completely dry, and so we have 4 months, more or less, in which we expect that the environment is related. I'm selecting this combination of bands. So on the air band, I will put the interferometric coherence. Then on the blue band, I choose an image belonging to the dry season that is the reference for my time series. And then on the green band, I will put my variable, so the image that I want to evaluate for my application. This is a representation of the environment. Here we can see that almost is completely dry. We have at the beginning of June, and then in August we have the environment that is full of vegetation. So this is my start through representation, and is this what I get using the band combination that I discussed before. Here I can see the green that is associated to vegetation, the blue that is associated to water, and these bright spots are villages. Now, this representation is probably close to the one I expect if I used to work with optical data, but the funny thing is that is physical building. Then the association between color and feature is stable because it is related to some backscattering mechanism. Let's see why. As an example, here I see green, and I said that this is related to vegetation, because if I put on the blue band, the reference band, so I expect that almost is completely dry, so I have a backscattering related to dry soil. Then when the environment is full of vegetation, and here my green band is acquiring during the wet season, I expect that there is an increase of the backscattering due to volumetric effect due to the presence of vegetation. So that's why I'm saying this green, because there is a high backscattering due to the presence of vegetation. When I see blue, basically during the wet season here, everything is covered by water. So what I'm seeing is the backscattering of the dry soil of the dry image, of the image acquired during the dry season. When I see black, this means that it is water that is present both in the wet and in the dry season, so the backscattering is compartment. The bright spots are villages, because when I have building, I have double bands backscattering, so I expect high amplitude in both images, and also high coherence, because the coherence is an indicator of the phase stability of the target, and usually buildings are characterized by high coherence. Then when I see a balance between the blue and the green channel, I'm basically dealing with the bare soil, so something that is unchanged between the two acquisitions. Here you can see the difference between a test using the wet season image and a test using an image acquired during the same season of the reference. So here it's almost completely dry, and I see a balance between the blue and the green channel. Okay, this is a way to use this kind of products. If I want to monitor the evolution of the water within this basin, I see that here on June it is full of water, then it starts to decrease, then we have both an increase in September, and I can reconstruct the cycle of this reservoir using a time series of bitemporal compositions. And I can also monitor the state of vegetation that I expect to increase when there is a lot of availability of water. Now, what is happening if I change completely the situation, moving from a semi-arid environment to a temperate environment? So we are here in Italy, the climate is temperate, so I expect a moderate availability of water lasting all the year. So here the scene is completely different. What is happening is that more or less the association between the features and the color is the same, because if I put as an example on the blue band an image acquired during winter, I expect in summer, if I use on the green band an image acquired during summer, to see growing crops in green. The water is black because it is unchanged and the backscattering is stable and low. I can see all the built-up area characterized by this white color. The red that you see is due to the fact that coherence is computed in wind, so you will have a green a red border around the building, and then everything is unchanged, is still characterized by a balance of blue and green. Now, you can say I don't like this image because it's too blue, and this is correct because the color is not very common in Mexico. So actually, this composition was studied to enhance the presence of water in semi-arid environment, but I can simply exchange the bands, so putting the coherence on the blue and the reference on the red in order to retrieve a significant red component on soils. And this is a representation that probably is more comfortable, more suitable for temperate environment, and something that is closer to what you expect if you are used to work with optical images. This is for bitemporal data. Let's see what we can do with multitemporal data. So can we build a composition exploiting all the time series? The answer is yes. In this case, of course, I have to change the temporal indicators. They are very simple time indicators. As an example, I can use the variance on the red band, the mean on the green band, and on the blue band, I can put a composition of the interferometric coherence that is useful to highlight buildings, and of the saturation index that is basically an indicator of the maximum span of the backscattering during the time series. And the composition that I get is something like this, in which buildings are cyan because the backscattering is stable and is high, so I have a significant green component, and is also coherent, so I have a blue component, so it's cyan. Pinkish colors mean that is something that is changing, that is in this kind of environment can be associated with crops. What is green? Just the contribution of the mean. So I have something that is unchanged. The sea is blue because I have here a significant contribution of the saturation index due to the backscattering. So I see this in blue. So also in this case, I can associate the color with the feature. And this is a nice view of a full sentinel SWOT in which I can understand where are cities. Here I can see crops, and what is green is basically forests or unchanged land cover. Of course, the level of the green can identify different features, because if I deal with forests, I probably will have a higher green component. With bare soils, probably I'm here, so I have a lower green component. It depends on the feature that I am considering. Now, let's see how we can use this kind of representation in operational environments. And let's start with an application. We come back to semi-arid environments. We want to evaluate the water availability in our reservoir. Based on our consideration, can you identify an index that can quickly deliver information about the presence of water in our reservoir? It is something similar to what we can do using optical data, because if I want to evaluate the presence of water in a basin using optical data, I can use the NDWI that is defined by green and near. Okay, green plus near. Using this kind of composition, we can do something similar. Can you guess how I can use the blue band that is the reference and the green band that is the test? to enhance the presence of water in my reservoir. Any suggestion? Any guess? No guess. Okay, let's go. Similarly to the NDWI, I can use as an example this formula in which I compare the blue band with the green band. Here I expect a significant backscattering because I want to see the backscattering of the soil is higher against the one of water, and then build an index that is similar to the NDWI. This coefficient is basically used to drop out medium melting component, but the rationale is similar to the one of the NDWI. And this is the results that I can obtain. Here I have my composition, then the change index, and then the segmentation that here is achieved using traditional thresholding, exploiting the fact that in the locally, if I compute the histogram around the reservoir, I will have an histogram that is basically bimodal, so I can distinguish what is unchanged from what is changed by putting a threshold on the local minimum of this function that is histogram. This is just to provide you an indication of the reliability of the method, which here I compared the accuracy about the definition of the contour of the reservoir using this kind of methodology and manually retrieved ground truth, and results are quite good. Once I have my contour, okay, so once I have identified my reservoir, if I have a digital elevation model that it's possible, if I use two images acquired during the dry season because the bottom of the reservoir is exposed, so I can retrieve the height using standard interferometry, I can combine the surface information with the height information to get the volume that is stored within the reservoir. And results are quite in agreement with those obtained from an hydrological model. When you see the highest differences, it is due to the fact that the reservoirs during the dry season are not completely dry. So there are areas in which I cannot retrieve the height because, of course, the soil is covered by water. So there is basically an underestimation of the water that is available within the reservoir. The problem is the thresholding, because to set automatically the thresholding is not trivial and is a topic that is highly debated in the literature. In this case, so I can move from traditional image processing to something that is more complicated, like rule-based system. And we will apply this kind of framework using a similar application. The phenomenology is almost the same because now we are dealing with flooding. This is the Albufera region in Spain that is now sadly known due to the recent flood. Actually, the Albufera is a natural reserve that is periodically flooded because here there are rice cultivations. So it is of interest to monitor the evolution of flooded area also because they are related to the growth of the rice. Now we want to set automatically the threshold using fuzzy rules. What is a fuzzy rule? A fuzzy rule is a way that allows me to classify data not using numbers but using verbal attributes. What does it mean? Let's imagine that we see a guy in the street. Oh, this guy is tall. But what do you mean with tall? 100 meter, 1 meter 80, 2 meters, 1.9 meters. It depends. So what I can do is to build a function in which I assign a probability that the guy is tall to his height. So I can say the probability that a guy is tall starting from, let's say, 100 60 centimeter, 170, 108. Here, probably in most of the cases, the guy is not tall, then the probability starts to increase. And then when I arrive at 2 meters, whatever the context, I can assume that the guy is tall. And in the same way, I can define a function for the probability that the guy is not tall. So this is the probability, low probability, and high probability that the guy is tall. I can do the same with my layers, with my SAR layers, okay? In this case, the layer I'm choosing are the change index and the post-event image. So I'm using one backscattering layer and one change detection layer. I put everything in my FACS system, and I require that the flooded area is characterized by high change index and low backscattering, using these functions that are that I am defined. These are mathematical functions that you can define to assign the probability. The funny thing is that now I don't need numbers to classify. I don't need to put a threshold, but I can classify the water surface, the flooded area, with verbal attributes. Okay, because now I'm saying high and low that are fuzzy. They are not very well defined, but they are defined using these functions. Okay. At the end, if I use 2 layers and 2 attributes, I will have 4 classes, because I will have class 1 that is high change index and low backscattering, that is the one that I'm interested in to identify. But I have also all the other combinations. So I have 4 classes that I have to defacify. So I have to decide what is the class that I want to assign to each pixel at the end of the process. You can use different techniques for these steps for making this, and the simplest one is to assign the maximum probability to each pixel. So I assign the class corresponding to the maximum probability to that particular pixel. Okay, this is a result on a test case in Ireland, if I remember. The problem is that when you use more layers and more attributes, you get this number of classes increasing. Okay, and this is difficult to manage where the number is where the number of layers or the number of attributes, because I can define low, high, medium high, medium low. So this can bring to the explosion of the rules that I have to define. So it's hard to manage with this. So in this case, I can move to some other kind of processing like machine learning. The technique that I want to show you today is a technique of data reduction, okay, that is related to the products that we are using. I'm presenting you the set organism map originally defined by Boone, and that in this case, it is used to reduce the amount of data, because when we have an RGB image, we have 256 to the 3rd power classes, okay, because each RGB treatment can be considered as a class. Okay, so you have a very large number of classes. Now we want to reduce this number of classes using a sum. How we can use this? We start from a set of neurons that are randomly initialized. Then we pick a color from our RGB image. We compare the color with our set of neurons. The closest color wins this race and updates the neurons that are in his neckbone. Okay, so if we repeat this process with a lot of neurons and for many epochs, for many times, we will get a map of colors that are the most represented in my RGB image. This is my starting point. So this image is continuous. So we are in a space of 2056 to the 5th power colors. And then we can get something that is like this, in which we have 49 classes. The funny thing is that now each pixel is not anymore associated to an RGB treatment, but to a color. Okay, here I have a list of colors. So I'm assigning a low-level semantics to my pixels. This means that the semantic, the class that I am assigned to the pixel, is not of a high level. So I'm not saying this is a river, this is a lake, this is a forest, or this is a crop. But I'm saying this is green, this is blue, this is white, this is red. That is not probably not the objective that we want to achieve, but it's something that we can use for further uses. As an example, how can I use my labels? I have these labels now. Okay, each pixel is associated with the color. How can I use these colors to classify the presence of water in my reservoir? The problem is still the threshold, because if I want to use traditional image processing, I have to define the threshold. If I want to use rule-based system, I have to define the functions. So there is a mathematical process that I have to define. Now, how can I use the labels to classify water? And I guess it is very, very simple. Okay, I will give you the answer. Basically, solving the difference. I see something on the chat. The sound will differ different function of an we will. I can give you quickly the answer. Of course, here the function that I'm using is the Euclidean distance between the neuron, the color that I'm presenting to the network, and the one that is within the zone. Then the function that you use to update the neighborhood of the winning neuron can be different. Here I'm using a band. So basically, the farther you are from the winning neuron, the smaller the effect on the neurons. You can make this band larger or thinner. Okay, this means that you are more influencing your the neurons that are in the nearby of the winner or not. It's choose. Okay, it's up to you how much you want to influence the neighborhood of the winner. You can use different functions for the things. Let's come back to our problem. I can use the labels to create a kind of dictionary of the classes that best represent water. I can do this with, as an example, with supervision. I can extract a region of interest within my reservoir, and I will find that most of the 90% of the histogram belongs to these classes. So blue, midnight blue, and royal blue. I'm using a database of HTML color, but you can use the database that you prefer. This is the map that I get. I see some noise. So the reservoir is quite well identified. I have some noise. I can also, with morphological filters, I can filter out most of the noise, and I can retrieve my reservoir, apply my reading. Okay, that is, as an example, the change index that we defined some slides ago. Actually, this is a preprocessing that allows me to move from the pixel world to the object world. So now I have to set threshold, but I'm working not anymore on pixels, but on the objects. So I can consider the average of all these clusters that is, of course, more precise to consider just pixels. Another application that we can face with this kind of products is, as an example, forest disturbances. In this case, I'm building a temporal composite, and I'm assigning to each pixel a class using the same processing. Instead, I have fully multi-temporal points instead of bitemporal points, but the processing is the same. So now I can quickly identify areas that are potentially affected by disturbances by setting a rule on the change of the color. I mean, if I have this situation, the starting situation in 2017, I can say, okay, let's extract all the pixels that are changing color from green to pink, let's say. And I can identify a series of regions that can be analyzed with the further processing in order to identify if they are really connected to disturbances or maybe there are some false alarm. As an example here, since I am close to a river, I think that this cluster, this pink cluster, that means that I have a high significant variance in saturation index. It is probable that it is due to flooding of these rivers. So I can use also the context to evaluate the clusters that I retrieved using this simple process. As I said before, now we are in the world of the objects. Of course, I can continue the series considering the images in carbon in order to evaluate potential disturbances in different fields. But what I want to highlight is that now we are in the world of objects. So we can use more tools to analyze our data using the clusters that we are identifying using these simple techniques. The reason why we do this is that if we consider just the pixel as an example, we are not able to discriminate between a river and a lake, because if we consider just the backscattering, here the backscattering is low, and here the backscattering is low. So the best you can do is to say, okay, this is water. But how we can assign a higher level semantics? So how we can say this is a river and this is a lake? We can use object-based image analysis. So we can define quantities that are related to the shape, to the context. So as an example, quantity is related to the shape, the compactness, that is the ratio between the area and the perimeter. Or the elongatedness, that is basically a measure of how much an object is elongated. This is because, as an example, a lake is very compact, so we have a high ratio between the area and the perimeter, and a river is not compact because the perimeter is much higher than the area. Okay. And using objects, I can also reason on the context. So I can put rules on the number of adjacent segments, how many segments are adjacent to one I have identified, if there are some other feature in the nearby, and so on. So I can put more complicated rules to extract higher level semantics. As an example, I want to count these the olive trees in this field. How can I do this? I can start from multi-temporal products and then starting to identify clusters that are characterized by these dark colors. Okay, I retrieve a pre-classification method, and then I applied object-based image analysis for calculating, as an example, the elongatedness, because basically trees are circles. So I expect that they are not elongated, but they are compact. So if I combine the pre-classification mask, the elongatedness, the compactness, I can basically build a decision tree to get my olive trees. Okay, this is the kind of application that I can face using this kind of processing. Now, it's almost lunchtime, 10 minutes, and we are almost at the end. Just a few words on AI. That is something that is useful to improve image understanding. Basically, we are putting everything together because now we are leaving to the machine to decide what are the features that should be computed. What are the most relevant to identify the object that I'm looking for? Okay, the first application that I'm presenting to you is the image domain translation. So I want to translate a side image to an optical one. That is useful, for example, if you are dealing with area characterized by massive cloud coverage. You can increase the availability of optical. What is done in the literature, okay, you can see here, is to act at the level of the architecture. Okay, I can define new layers, new architecture, new cost functions. So I'm playing with the net. But what is not done is to play on the input. Okay, because now here we are using, as in the most of the literature, SRC data. So we are translating speckle. And the speckle is random. So if I consider the same feature, it can appear differently in different acquisitions. Okay, and this can make the depth confusing because now we are using generative methods. Okay, and to be honest, here I can see also some problem of equalization in the optical data. And in my opinion, it is important that both the input and the output and the target are as close as possible in order to facilitate the translation process. This is the results that are provided by the literature. We have some indicator like the peak signal to noise ratio, the structural similarity index. You can define some quality measure for our images, and we see these numbers, 18, 0.89, that are fake. Okay, what we can do is, can we do something more or something better? Just playing on the input and the output. No work on the net. We are using now very standard architecture that is also used here, the pix-to-pix, the pix-to-pix net that is very popular net, and also the very basic one of the first GAN that has been proposed in the literature. And we are just playing on the input because now we are using one bitemporal product, okay, targeting the optical image, possibly with a good equalization in order to make everything homogeneous. This is the input, this is the target, this is the output that is somehow similar to the input, and this is a difference map between the colors. And what I get is that I can increase the quality parameter of the image because now we are almost at 30. The structural similarity that is a perceptual metric is also increased. So we can do much better of the literature just playing on the input. This is a picture of, I merged basically the native optical image with the generated one. This is the native, and this is the generated, just to show you that things are almost homogeneous. Okay, so we have a good matching between the SAR, the translated optical, and the native optical. How can I use this kind of products? As an example, I can estimate the NDVI. This is, of course, an RGB image, so we can use just optical bands, so the other GMB. Here I made a regression using optical, native optical images, so this is retrieved from RGB bands, and here I use this RGB. Results are fair. Actually, this net is not much trained. I didn't use many patches because, of course, you need a significant computational power for making this kind of application, but this is just a first indication that this kind of products can be used also in applicative settings. Last topic, band area detection, the same. We are working at architecture level using a very basic input. This is what is proposed by the literature. Basically, we have a post-event SAR that is translated into a post-event optical. From this, the post-event optical is a composition of basically near and shortwave infrared that are the quantities that are used for computing the NBR, that is the index that is usually exploited for mapping the band index. Post-event SAR on post-event optical. But in this framework that is fair results, I see one problem and I have one question. The problem is the inconsistency of SAR amplitude response in the pre and post event phases. And the question is really the post event multispectral image the best option? Now, the question that I want to propose to you is, can you guess why the SAR response is inconsistent between the pre-event and the post-event phase? Because if I have this situation, this is my tree, I expect that after the event, the canopy is removed. So what I expect is that the backscattering decreases because I don't have any more the leaves that triggers volumetric backscattering. But it can happen, it has been demonstrated that it can happen that when the canopy is removed, you can trigger double bands response between the branches. Okay, so the backscattering can increase in the post-event phase. And also, you can have the effect of the soil, because if you pour water on the fire to drop out the fire, okay, the soil now is wet, and you have the effect of the dielectric constant. And this also can happen in case of rainfalls. So at the end of the day, the backscattering can increase or can decrease. It depends, and we can forecast it. So if I use just the amplitude, I can get confusion in the net because I have this ambiguous behavior. As for the translation target, why don't we use the post-event NDF? Now we are using, in the literature, we are using the post-event multispectrum, but we can use also the NDF. So we can target directly a coherent composition. So I have both amplitude and phase because the phase is stable. I can see, can you see here, the coherence is constantly decreasing in the post-event phase because the distribution is changing. The coherence is an indicator of the stability of the scene. When the scene changes, the coherence decreases, and this phenomenology is stable. So I can exploit coherent composition and target it directly on the NBR to obtain the post-event NBR that I can use with the pre-event NBR for the arbitrary. And in the last row here, you can see the difference that is quite good. This is to show you what happens using the coherence. Here, I'm using an undisturbed scene with a post-event scene. This is a long fire, okay? So I want to monitor, I want to follow the fire as long as it is active. Okay, so T0 is an image acquired when there is no fire. Then I have the fire. I can see here the coherence that is dropping. Then the coherence here is restored because now the scene is unchanged. Because if I consider two images taken when the fire is active, here is everything bound, so the coherence is stable. But I see the fire that is moving. And when everything is stopped, so when the fire is closed, I can see that the coherence is restored throughout the scene because everything is unchanged. This is in amplitude. And as you can see here, I cannot see many differences between the pre-event phase and the post-event phase. So this is to say that the coherence now is much more informative than the amplitude. If I put everything together, amplitude and phase, I can see that I can delineate quite well the area of the fire against the truth provided by the optical. This is just some results on some cases that I analyzed. This is a difference map between the generated difference and the art difference and the native one. Actually, you have a lot of noise using this kind of approaches because the relation between the difference of the NBR between the pre-event and the post-event is quite strict. So you have it is possible that you have the water that resonates with with the index, but you can filter out using, again, some rules on the average of the cluster. You can use the context. I mean, in most of the cases, you can polish your method, getting very good results in agreement with the optical graph. Summary, we are at the end. So we have seen very briefly how multitemporal SAR can be used for environmental monitoring. We can use data, multitemporal data, to build user-friendly composition that are useful for visual data management and also for processing. We explored different ways to process this kind of data. And just a comment, AI is the present and the future, of course. Black boxes are fine, but let's try to use it taking in mind what kind of data we are using. I mean, we should try to respect SAR data, and we can design some more reliable processing strategies for this kind of peculiar data that can bring us to good results. Okay, I think I'm almost on time. 50 minutes. Okay.